Okay, come on. You gotta go. You gotta go. Come on. Come on. Go. You gotta get out. Go. Come on. Go. Henry, you gotta go. Don't play with my foot. You gotta get. Sorry, you gotta go. Got him. All right, welcome back. I did look at I only had one comment on my e-learning video. Thank you to whoever you were, Meep, who commented. I feel like such a failed YouTuber. One comment. It's okay. The intro with the cats is a great idea. I just don't know how to do that. Like how to film an intro and then edit it into the beginning of every video or something. So I'm looking more along the lines of like a line that I say at the beginning or a line that I say at the end to finish all my videos. Just something I can say, but I don't have to edit in there. So anyways, this is it. We are going to finish off Unit 3 today with Section 3.6. And then after this, it is test time. So let's see if we can get this darn thing to focus. We've been having a lot of luck with it focusing first try every time. Let's see, I should not have said that. Yes, okay, cool. So here we go. In lesson 3, we're gonna learn about even and odd functions. And so we call that function symmetry. Now on this first page, you will notice that there are 3 graphs here that are symmetric over the y-axis. That if you fold the graph one side of the y-axis over, you fold it over the y-axis, it'll fall on top of the other side. So this in geometry is what you call reflectional symmetry. See, all that geometry stuff really was important. And f of x has this symmetry, and so does p of x, and so does q of x. And all 3 of those graphs have that reflectional symmetry. They are all symmetric over the y-axis. So it's f, p, and q. On the next page, it wants us to write down all of the functions that have y-axis reflective symmetry. So that was f of x and p of x and q of x. Okay, we've recorded those. Now let's go back to the other side, and the other 3 graphs do not have that reflective symmetry. They have what you called in geometry rotational symmetry. They are all symmetric about the origin. And so if you kind of keep the origin constant and rotate this 180 degrees about the origin, you have the exact same graph. And that is true for these 3. If you rotate them upside down, the graph looks exactly the same. Rotate it upside down, graph looks exactly the same. You also probably said in geometry that these have point symmetry. That is a correct way to say that. All right, so those were g of x, h of x, and r of x. So g, h, and r. So on the next page, we have functions with origin rotational symmetry, g of x, h of x, and r of x. Now I'm just going to flip back just because there's some directions here on this page before. It says in the boxes on the next page that we are supposed to list all of the specifically plotted ordered pairs on the graph and list them in the order that they appear from left to right. So we're going to go through f of x and we're going to list, and I'm going to go ahead and use this beginning point here where the arrow is and the ending point there where the arrow is as well. And we'll list -6, 3, -4, 1, -2, -1, 0, -3, 2, -1, 4, 1, and 6, 3. And we're going to do that for all 6 functions. We're just going to list all of their ordered pairs here. I am not going to keep this video running while I go through and do that. You can go ahead and do this. I'm going to do it. and then I will pause, and then if you don't pause your video, then magically all mine is going to be finished. So I suggest that you go ahead and do that as well. Pause the video, and then when you're ready, unpause it again. So here we go. I'm going to list the ordered pairs for all 6 of these functions, and I'm pausing on 3. 1, 2, 3, pause. And just like that, it's magic. We've got all of our ordered pairs written down. Okay, we're just going to look at these ones with y-axis reflective symmetry, and we're just going to notice a pattern here. And you might have kind of noticed this pattern on your own, and you might have found that the points at the end, you maybe didn't even need to look at the graph to be able to get those points. And if you were able to get there, that's great. So I'm going to kind of, this point that's on the y-axis kind of separates these are the points to the left of the y-axis, and these are the points to the right of the y-axis. And what I want you to notice in every case here is that these y values kind of don't change, right? We got these points with a y value of -1, these points with a y value of +1, and these points with a y value of +3. Let's just look at the x coordinates of those points, okay? -2, +2, -4, +4, -6, +6. And that happens in all of these other ones. If we look at the points with the same y value, look at that, opposite x values. Same y value, -2 and 2, opposite x values. Same y value, x values are -3 and 3. Same y value, x values are -6 and 6. And it happens here as well. -1 and 1, -3 and 3, -5 and 5. Those pairs of points, they'll have the same y value. So what's occurring here is that if we change the sign on the x coordinate, the y coordinate stays the same. Right? If you look at -5, 4, well, if we change the -5 to a +5, the y coordinate is still 4. -1, -2. Change the x coordinate to +1, the y coordinate is still -2. This is going to be the case for all y-axis reflective symmetry functions. I'm going to go to the next page here, and it says numerical and graphical definition of even and odd functions. Now, I haven't used these words even and odd yet, but I'm going to now. An even function is the y-axis reflective symmetry. And actually, I should have just written that here. The graphical definition would be that an even function is symmetric over the y-axis. So those 3 functions, f, p, and q, we say that they all have even symmetry. They have even symmetry, or you're going to say they're even functions. They are symmetric over the y-axis. Now, numerically speaking, if you change the sign of the x coordinate, the y coordinate stays the same. So if xy is on the graph, then you're going to have another point with the same y coordinate, but the opposite of the x coordinate. So we're thinking about this numerically. Another way to write this down is using function notation. And that is to say that f of x will equal f of -x. Remember, f of x means the y value. So this means whether your x is x or -x, if you change the sign on the x value, you're going to get an equal y value. If you perform the function on the x value, or you perform the function on the opposite of the x value, the y coordinate is going to stay the same. This rule is going to be important to us. So you need to make sure that you know that rule. That's kind of the analytical rule for a even function. So I would say this is graphical, this is numerical, and then this is sort of analytical here. So we've got all 3 forms identified. Now, if we look at the other ones, the red ones, you'll notice that the same thing doesn't happen. I'm still going to kind of separate things here by the origin. This one didn't have an origin, but that's okay. You can still separate the top 3 and the bottom 3. And I want you to compare these points. Now, if I change the x value of -2 to a +2, look what the y does. The y changes as well. If I change the x from -4 to +4, the y changes from -3 to 3. So now, when I change the sign of the x coordinate, I'm also changing the sign of the y coordinate. And that's what gives us that 180-degree rotational symmetry. It's the same thing here, -2, 2, -1, 1, -3, 3, -4, 4. It's the same thing over here. The -1 changes to a +1, the -2 changes to a +2. These are what we call odd functions, and they are symmetric, or they are symmetric about the origin. I'm just going to make a note here that that is rotational symmetry. You rotate it 180 degrees about the origin, it's the same graph. Numerically speaking, if you have a point on that graph whose coordinates are x and y, then you're going to have another point with the opposite of the x value and the opposite of the y value. You can kind of compare those two numerical rules. With even, if you change the sign of the x, the y stays the same. With an odd function, if you change the sign of the x, you also change the sign of the y. Okay, so for my analytical definition, I'm going to write it this way. F of minus x equals minus f of x. Now remember, the f of means y value, right? When you do f of your input, you've now produced a y value. So you notice that the x is changing from -x to +x. But now, after we perform the function, the outcome will be the opposite. Remember, that doesn't mean it's going to be negative. It means if it was positive, now it's negative. If it was negative, now it's positive. Okay? So this really means if you change the sign of the input, you're going to change the sign of the output. So minus f of x means your y value will change to the opposite. Okay, now you can see they have our rule right here for an even function, f of minus x equals f of x. I think they've got it kind of backwards from the way that I wrote it, but it's the same idea. And so we want to kind of identify, are these even functions? So let's go ahead and do that by using our rule for an even function. Let's see. It doesn't really give a question here, but what I want to see is f an even function? If it is, this rule will apply. Now, I already know what f of x is. I've got it right here. What I need to find is f of minus x. And this is really easy to do. All we need to do is replace these x's with negative x's. So I'm going to recopy this whole function to absolute value of 3. And instead of 3 times x, it's 3 times negative x. And instead of x squared, it's negative x squared. See, I replace the x's with negative x's because I'm finding f of negative x. Now, as I continue to try to simplify this thing, 3 times negative x is negative 3x. And if I square a negative, the negative will become positive. So we've already kind of gotten rid of that negative there. Now, the other thing is that if you do the absolute value of a negative, it's the same as doing the absolute value of a positive. The absolute value of negative 3x is the same as the absolute value of positive 3x. Just like, for instance, the absolute value of negative 5 is equal to the absolute value of positive 5, right? And they're the same thing. So I can kind of remove that negative, and looky here, that is exactly the same as f of x. So I have shown that f of x is equal to f of negative x. I plugged in negative x and I found, well, that really simplifies to the same thing as f of x. So yes, f of x is even. Let's try it with this guy here. I think this one is a little bit more obvious, but when I find g of negative x, that'll be 2 times negative x to the 4th plus negative x squared. And it's not just squaring negatives that turns things into a positive. Any even exponent will turn your negative into a positive. So negative x to the 4th is the same as positive x to the 4th. And negative x squared is the same as positive x squared. And looky there, that is exactly the same as g of x. So yes, g of x is even. There's just 2 examples there. Okay, now this wants us to use our graphing calculator to sketch the graph of this and then use that graph to determine whether P of X is even or odd. You can go ahead and do that if you have your graphing calculator with you. If not, I'm going to go ahead and just do it now, and you can just use my graph. Okay, so it's going to look something like this. I don't want you to get intimidated. This is not a graph I would expect you to be able to come up with on your own at all at this point. That's why it said use your graphing calculator. And I don't think I did a great job of drawing it there. I did okay, but hopefully you can kind of see how that does. It is symmetric over the y-axis. You take the part on the right side of the y-axis and reflect it over, it's the same graph. So it is symmetric over the y-axis. So we're going to anticipate that this would be an even function based on the graph, but we see those odd exponents in there, and it seems like, how can this be an even function? Well, let's see if it is. So the way we do that is we start by finding P of negative x, which means we'll have negative x cubed on top. On the bottom, this x will become a negative x minus 2 times negative x to the 5th. Then let's see if we can do some simplifying here. Now, if you cube a number, if you do negative x times negative x times negative x, the negative times negative times negative is going to result in a negative, and the x times x times x is going to result in x cubed. So really, I can just kind of get rid of that parentheses there, and I have minus x cubed. Now, on the bottom, I've got a negative x, and I'm subtracting, let's see here. It's kind of the same thing. When I do a negative x to the 5th, I've got 5 negatives there, so I know my answer is going to be negative. If you do negative x to the 5th, that's going to be a negative number. And then we're multiplying that by negative 2. So we're kind of multiplying 2 negatives here, which will cause that to be a positive. Okay, so I don't have any more negative here because I used the negative from the negative x to the 5th to change this to a positive. All right, now I want you to watch kind of what I'm going to do here. I'm going to multiply the top and the bottom of this fraction by negative 1. That is a legal thing to do because negative 1 over negative 1 is equal to 1. Right? Any fraction where the numerator and denominator is the same, that fraction is equal to 1. So I'm really multiplying by 1. Multiplying by 1 might change the way something looks, but it doesn't change its value. So in my next step, a negative x cubed times negative 1 is a positive x cubed. On the bottom, negative x times negative 1 is positive x. Positive 2x to the 5th times negative 1 is negative 2x to the 5th. And notice that that is exactly the same as P of x. So we have shown that P of negative x is the same as P of x, and therefore we have an even function. Okay, next page. Analytically, a function is odd, and there's our rule for an odd function. Notice that we still have to find f of negative x, but now I'm not trying to see if f of negative x is equal to f of x. I want to know if f of negative x is equal to minus f of x. And really, guys, all I'm going to do is I'm just going to find these two things. So I'm going to start by finding, for this example, I'm going to start by finding f of negative x, right? Because that's the first piece that we need. So this 3x will be 3 times negative x plus, and then the x cubed will now be negative x cubed. All right, if you multiply 3 times negative x, you get negative 3x. And then if you cube a negative, you're going to get a negative. So that'll be minus x cubed. So there's f of negative x. Now I need to find minus f of x. Okay, because now the other piece is minus f of x if we're testing to see if the function is odd. Before I do that, I think I should point out that it's definitely not even. Look, here's f of negative x. Here's f of x. Those are not the same thing. So this is definitely not an even function. Let's find minus f of x, and that's easy. It means we take the whole f of x function and we make it negative, right? Minus f of x. And now if I distribute that negative, I'll have a minus 3x, and the negative 1 times x cubed is minus x cubed. And look at those two expressions. They are absolutely the same. So we have shown that f of minus x is equal to minus f of x, and that means that this is a function with odd symmetry. Let's do it with g of x as well. So let's find g of minus x. So I'll do 2 times negative x minus, and then this x becomes a negative x. And then I've got an absolute value of 2 times negative x. Okay, so I'll still have that subtraction there, and then that x becomes negative x. Let's simplify this a little bit. 2 times negative x is negative 2x, and now subtract a negative x, and it'll be a positive x. Now, inside of my absolute value here, this 2 times negative x is going to be a negative 2x. And we talked before about doing the absolute value of negative 2x is the same as doing the absolute value of positive 2x. Now, I found g of negative x. Is this the same as g of x? Not exactly. So g of x is not even. Okay, well, let's see if it's odd then. Let's find negative g of x. So the way that we do that is we take our g of x function, we just copy down that g of x function, and then we make the whole thing negative. So minus g of x. Now, if we distribute that negative, I'll have a negative 2x, and then a negative 1 times this negative, we'll turn that to a positive. And then again, you can notice that this expression and this expression are exactly the same. So again, we have shown that g of negative x is equal to negative g of x, and so therefore this function as well is odd. Okay, so we've seen some even examples, we've seen some odd examples. Let's kind of look at 2 more here real quick, and we don't know whether these are even or odd. So with f of x, first let's test and see if it's even. Remember, the even rule is f of x equals f of negative x. So we've already got f of x here. Let's find f of negative x and see how that works out. So that would be 3 times negative x squared plus negative x. Now, if we square this negative, it'll become positive. So that'll be positive 3x squared. And then adding a negative x will just be minus x. Okay, is that the same as f of x? Nope, it's not. That means this function is not even. Okay, well now let's check and see if it's odd. So we know that our odd rule is that f of minus x or f of negative x equals negative f of x. Now luckily we've already got f of negative x, right? So we don't have to do that again. All we need to do is the negative f of x. So negative f of x equals, so we're just going to put a negative on the whole f of x function. And if we just distribute that negative x, we'll get minus 3x squared and minus x. All right, is negative f of x the same as f of negative x? No, it's not. This is not odd either. So this one is neither even nor odd. Now the truth, guys, most functions don't have even or odd symmetry. Even and odd symmetry is a special thing that a function might possess, or a special property that it might possess. And that's why it's worth knowing about. It's not that common. And so when it does happen, it's like, oh, we have a special way that we can deal with these functions, or we know a little bit more about them. We know how their graph is going to be symmetric, or we know numerically if I change the x value, what's going to happen to the y value. We can do a little bit more predicting, and it makes them easier to deal with if we know that they have symmetry, because most functions don't. Here's another one. Let's test this one out. Let's start by finding g of negative x. So that would be 2 times negative x times the absolute value of negative x plus negative x squared. All right, now look, the absolute value of negative x is the same as the absolute value of x. 2 times negative x is negative 2x. Then I'm adding, and if you square a negative x, squaring a negative turns it positive, so it's just plus x squared. Now, is g of negative x the same as g of x? Nope. G of negative x is not the same as g of x. Therefore, this function is not even. Okay, well, let's check and see if it's odd. We know the rule for odd. We've already got g of negative x. We just need to find minus g of x. So I'll put a minus and then in parentheses my whole g of x function. All right, so here if I distribute the, what did I do that for? There should not be a parentheses here. It should be there. If I distribute my negative to this first term, it'll be minus 2x absolute value of x. Distribute the negative to the next term, it'll be minus x squared. So here is minus g of x. Is that the same as g of negative x? No. G of negative x is not the same as negative g of x. So also, this is not odd. So that's kind of the most common situation. We've got one more down here to do. I'm going to go ahead and graph this on my graphing calculator, and you'll see the picture magically pop up here. Okay, so the graph looks something like this. I don't know if I did a very good job of drawing the picture or not, but you're supposed to notice that it does have that rotational symmetry. Same graph that way as it is that way. And so it should have odd symmetry. Let's go through and just see if it does. So odd means p of negative x equals negative p of x. Let's test it out and see what happens. So p of negative x would be 2 times negative x minus 3 times negative x cubed. On the bottom, we'll have 2 times the absolute value of negative x. Okay, you multiply 2 times negative x and you're getting negative 2x. Now, if you cube a negative, you're going to get a negative. So this is negative, and then we're multiplying that by negative 3. So we'll have a negative times a negative, which will make a positive 3x cubed. On the bottom, I've got my 2, and then the absolute value of negative x is the same as the absolute value of positive x. Okay, here's p of negative x. Is that the same as p of x? Definitely not. That means the function's not even. Okay, we're kind of checking to see if it's odd. So for odd, we also need to have negative p of x. So that means I'm going to take my whole p of x function and make the whole thing negative. Now the idea is, can I use legal algebraic moves to make this expression simplify to this one? The deal is we got this negative on the outside of the whole fraction. Do you see, though, how this denominator is the same as this denominator? So what I really want to do is apply this negative to the numerator. And I'll just remind you that when we deal with fractions, you make like negative 3/4. That's the same as putting the negative on the top and calling it negative 3/4, or putting the negative on the bottom and making it 3/-4, right? You can put the negative on the top or on the bottom or out in front. Right now, we've got the negative out in front, and I want to put that negative on the top. So I'm going to leave the denominator the same, and I'm just going to distribute the negative to those terms in the numerator. So negative 2x, and then a negative 3x cubed makes plus 3x cubed. Okay, there's negative p of x. And is that the same as p of negative x? Absolutely, they are identical. So I have shown that p of negative x is equal to p of x, and therefore this function has odd symmetry. Excellent. There we go. That's the end of Unit 3. We did it. I'm going to let you go there. So snappy tag offline here. Later.